Welcome back to the Deep Dive. Today, we're heading deep underground, figuratively speaking, to wrestle with a really tough computational problem in the energy world.
We're talking about understanding how fluids, like oil or water, move through fractured rock.
And this isn't just some academic exercise. There are huge economic implications here. I mean, something like 65% of the world's oil reserves are found in these naturally fractured reservoirs.
That number really says it all. Getting simulation right isn't just nice to have. It's absolutely critical for figuring out how to recover as much of that oil as possible.
So engineers use this framework, right? The Discrete-Fracture-Matrix model, or DFM?
Correct, DFM. The idea is you treat the main rock body, the matrix, as one thing, and then these fractures, these cracks that act like little highways for the fluid, as separate, lower dimensional things embedded in it.
Okay, conceptually that makes sense. Matrix stores, fractures transport fast. Darcy's law for the rock itself.
Yeah.
But where does it get complicated?
It gets really complicated when you try to actually build the computer model, the mesh. Generating that computational grid, the finite element mesh, for these complex fracture networks, it's a nightmare.
A nightmare how? Like too much detail.
Well, yeah, that's one problem. You can end up with an incredibly fine mess. Billions of points. It takes forever to compute, costs a fortune.
Okay, so that's one issue. What's the other side of the coin?
The other big problem is you get these terribly shaped elements. When two fractures are almost touching, the meshing software has to create these incredibly thin, long, stretched out elements in the matrix between them.
Ah, the sliver elements I've heard about.
Exactly, sliver elements. And they are poison for numerical stability. They completely mess up the calculations.
So you're stuck. You either have a mesh that's too big and slow, or one that's got these sliver elements that make the whole simulation unstable.
Precisely. You need a certain element quality for stability, but the real-world geometry sometimes forces these tiny, problematic shapes. It's a fundamental conflict.
Okay, so this deep dive is all about a really neat way around that conflict. A new approach that sort of leans into the problem.
That's a good way to put it. The core idea is to say, okay, what if we intentionally allow some geometric inaccuracy? Specifically, letting fractures that are very close actually overlap in the computer mesh.
Overlap. But doesn't that break the physics? If they overlap, isn't the rock between them just gone in the model?
It would break the physics, yes, if that was the end of the story. But the key is they combine this geometric compromise with a very specialized mathematical treatment.
Ah, okay. So the geometry isn't perfect, but the math fixes it.
Essentially, yes. They use a specific type of method called the mixed finite element method, mixed FEM, which is locally conservative and stable. This allows them to handle the physics correctly, even with the overlapping geometry.
Sounds clever, like accepting one problem to solve a bigger one. So let's dig into that foundation. Why mixed FEM? What makes it so special for this?
Well, standard methods can struggle sometimes, especially in these really varied, heterogeneous rocks. It's hard to get both the pressure and the flow rate accurate and conserve mass everywhere.
Okay.
Mixed FEM is designed differently. It uses something called HDiv conforming flux approximations.
Okay, that sounds technical. What does HDiv conforming actually do for us, practically speaking, for the fluid moving underground?
Think of it like this. The method is built from the ground up to focus on the flow rate, the flux across the boundaries of every little computational block or element.
So it's tracking the flow in and out of each piece very carefully.
Exactly. It guarantees that the amount of fluid going into one side of an element perfectly matches what comes out the other side, accounting for any sources or sinks inside. It enforces mass balance locally.
Not just overall, but block by block.
Correct. And that gives us two vital properties. First, for incompressible flows like water, it strongly enforces that the flow is divergence-free. No fluid just vanishing or appearing out of nowhere.
Makes sense. And the second property, you said it was critical here.
The second, and the absolute key for this work, is local mass conservation.
Why is local mass conservation the linchpin? Why is it so important that it's conserved right there in that specific spot?
Because reservoir simulation is almost never just about flow. You immediately want to couple it with other physics. Think about heat, for example, injecting steam.
Right, thermal recovery.
If your flow model loses even a tiny bit of fluid mass in one of those sliver elements, or anywhere else, when the heat calculation comes along, it sees that mass is simply gone. Poof. Your temperature calculations, your energy balance, it all gets corrupted downstream.
I see. It's like balancing your checkbook. If you misplace $1 early on, your final balance will be wrong. You need every transaction accounted for locally.
Exactly. This method provides that sort of ironclad guarantee, mass in equals mass out at every single interface. It's non-negotiable if you want stable results when you start adding complexity like heat or chemical transport.
Okay, so mixed fem gives us that rock-solid, locally conservative foundation. Now, back to the meshing problem. You mentioned they use an algorithm called DFN mesh.
Yes, DFN mesh. It's designed specifically for these DFM problems. It takes a coarse grid of the main rock matrix and then inserts the fractures one by one.
And it has a snapping feature to avoid the sliver elements.
Right. To keep the mesh elements well-shaped and avoid those unstable skinny ones, it uses tolerances. If two fracture parts, or a fracture and a mesh point, get closer than a certain distance, let's call it epsilon.
A tiny gap.
The algorithm basically says, okay, these are too close, let's just snap them together. Merge them, connect them, instead of trying to squeeze a tiny element in between.
And there's an angle tolerance, too, epsilon alpha.
Yes, for handling intersections cleanly. But the unavoidable trade-off is there. Either you set those tolerances really, really small to capture the exact geometry.
Oh, and you get slivers and instability.
Or you relax the tolerances, allow more snapping, and you get a nice, stable, probably coarser mesh.
But relaxing the tolerance, allowing that snapping, that's what leads to the potential overlap, right? If two fractures were originally very close but separate.
That's the direct consequence. If they're closer than epsilon, the snapping makes them overlap in the generated finite element mesh. And like you said, the bit of porous rock that should have been between them just vanishes from the geometric model.
Okay, so you've gained mesh stability, but it looks like you've broken the physics by deleting that piece of rock.
Yeah.
How do they fix that specific problem? This seems like the core innovation.
It really is. The paper introduces what they call a novel constitutive treatment. Think of it as a targeted mathematical fix applied only in those regions where the snapping caused an overlap between, say, fracture I and fracture J.
So they're not trying to rebuild the mesh geometry. They're adjusting the equations in that specific overlapping zone.
Precisely. They add a new flow term, a new flux variable, let's call it UI, and this term is specifically designed to represent the fluid exchange through the matrix rock that was geometrically deleted.
Okay, so they're mathematically putting the rock back in. How do they figure out how much flow should have gone through that missing rock?
They look back at the original geometry before any snapping happened. They use the pressure difference between the two now overlapping fracture pieces in the mesh.
Okay.
They use the permeability, the hydraulic conductivity of the matrix rock that should have been there, let's call it Ka.
Right, the rock's ability to transmit fluid.
And crucially, they use the actual physical distance, Dij, that separated those two fractures in the real original geometry.
So they use the real distance, not the zero distance implied by the overlap in the mesh.
Exactly. And the equation for this restored flex is basically Darcy's law for that missing piece. Ka times the pressure difference divided by that original distance, Dij.
Wow. So the calculation ignores the flawed mesh geometry at that specific point and uses the original physical reality instead.
That's the elegance of it. You get the computational benefit of the stable, possibly overlapping mesh, but you retain the correct physical interaction governed by the matrix properties and the true separation distance.
It effectively decouples the need for perfect geometry from the need for accurate physics,
making the whole simulation approach much more robust and practical. You can use coarser, more stable meshes without sacrificing the essential flow physics.
Okay, the theory sounds compelling. But does it actually work? We need to see the proof. Let's talk about the validation cases. They started simple, right? Two horizontal fractures.
Yes, a very clean test case. Two horizontal fractures. And depending on how they set that snapping tolerance epsilon, they could make them either stay separate, high-fidelity mesh, or overlap, coarser mesh.
And the goal was to see if this new mathematical treatment on the overlapping mesh could replicate the results from the accurate non-overlapping mesh.
Exactly. And they tested 3 scenarios for that matrix permeability term, Kij, in their special flux equation for the overlap zone.
What were the 3 scenarios?
Okay, scenario 1. Use the actual permeability of the matrix rock that should be there. This is their proposed method.
Makes sense. Scenario 2.
Scenario 2. Set Kij to be really, really large. This basically simulates perfect connection, like the fractures are touching with no resistance. It shows what happens if you ignore the matrix resistance entirely.
Kind of like assuming infinite permeability between them because they overlap.
Right. Maximum possible exchange. And scenario 3 was the opposite. Set Ka to be very, very small. almost zero.
Simulating no connection at all, like putting impermeable concrete between them.
Pretty much minimal exchange. This shows what happens if the overlap effectively blocks the flow path that should exist through the matrix.
Okay, 3 tests. Actual permeability, way too high, way too low. What did the flow results show when compared to the high-fidelity, non-overlapping case?
The results were, well, really convincing. Only scenario 1, using the actual matrix permeability in the treatment, produced flow results that showed great agreement with the high-fidelity simulation.
Ah, so their method worked.
Yeah.
What about the other 2?
Scenario 2, the large K value clearly overestimated the flow. Fluid just zipped between the fractures too easily, ignoring the rock's natural resistance.
As you'd expect.
And scenario 3, the small K value, clearly underestimated the flow because the model incorrectly blocked the natural pathway through the matrix.
That's a very clear validation. It shows that correctly modeling that matrix interaction, even when the geometry is compromised, is essential. And their method does it right.
It really isolates and proves the core concept. You're accurately restoring the physical resistance of the porous medium.
Okay, that handles the simple case. But what about a more realistic, complex situation? They used a benchmark problem too, right?
Yeah.
With 8 fractures.
Yes, a standard 3D benchmark problem, a network of 8 intersecting fractures. This is where geometric complexity and potential errors from snapping would really start to add up.
And they created different meshes for this, ranging from super accurate to quite coarse.
Exactly, 4 meshes. Case A was the reference, extremely fine, high geometric fidelity, probably expensive to run. Then cases B and C had progressively more relaxed snapping tolerances. And case D used the most relaxed tolerances.
So case D would have the coarsest mesh, the most potential overlap due to snapping, but should be the fastest and most stable to compute.
Correct. Case D is the most geometrically compromised but computationally efficient one.
So the big question, could case D, with all its geometric flaws but with a special constitutive treatment, still produce accurate results compared to the perfect case A? What did the pressure look like?
They looked at the hydraulic head, which is essentially the pressure map across the whole domain, and remarkably, the pressure variations were captured very well even in case D.
Really? Even with the coarse overlapping mesh?
Yes. The overall pressure field didn't degrade significantly just because the geometric details were simplified.
That's impressive. But the ultimate test, given the reliance on mixed FEM, has to be the mass balance, right? Did the fluid volumes add up correctly?
Absolutely. That's the critical check. They did a detailed breakdown looking at the flow rates, the fluxes going into and coming out of each of the 8 fractures. And they did this for all 4 mesh cases, A, B, C, and D.
Okay, comparing the perfect mesh A to the flawed mesh D, what was the verdict on the fluxes?
This is the most striking result, I think. The total sum of all incoming and outgoing fluxes across all fractures was numerically identical for all 4 cases.
Identical. So case A and case D had the exact same overall fluid balance.
Numerically identical. It's a powerful demonstration that the combination of the locally conservative mixed FEM and their constitutive treatment for overlaps perfectly preserves the mass balance, regardless of the geometric simplification.
That's huge. It means the method is totally consistent and reliable from a mass conservation perspective.
And it gets better if you looked at the bigger picture, like at the total flow crossing the boundaries of the entire reservoir model.
Yeah.
The difference in that total flow between the super accurate case A and the coarse overlapping case D was only about 2%.
Wow. Only 2% difference in total throughput, using a much simpler, faster, more stable mesh.
Exactly. It suggests engineers can confidently use these computationally cheaper models and still get results that are well within acceptable accuracy for making important decisions.
This really does feel like a breakthrough then. They faced this computational deadlock, unstable geometry versus inaccurate physics, and found a way to sidestep it.
By strategically sacrificing some geometric detail, but rigorously enforcing the physics using mixed FEM and that clever constitutive treatment for the overlaps.
They essentially solved the meshing bottleneck for these complex systems.
I think that's fair to say. The key takeaway for you listening is that this combined approach lets engineers move away from needing these incredibly detailed, often unstable geometric models.
They can use coarser, stable meshes instead.
Yes, meshes that are much easier to generate and cheaper to run, while still getting results that are physically accurate and, crucially, that conserve mass perfectly at the local level. It really streamlines the whole simulation workflow.
So, thinking ahead, what's the big implication of having this robust, locally conservative method even with simplified geometry? Where does this lead?
Well, the fact that they've locked down local mass conservation is everything. That robustness, that reliability, it's the absolute prerequisite for tackling more complex coupled problems.
It's like the heat transport you mentioned earlier. Or other things.
Exactly. Think about simulating thermal EOR with steam injection, or modeling how CO2 migrates and gets trapped during carbon sequestration projects, or tracking different phases, oil, water, gas moving together.
Multi-phase flow. Yeah, that gets complicated fast.
Hugely complicated. And in all those cases, stability and ensuring mass and energy or component masses are perfectly balanced is non-negotiable. If your underlying flow model isn't perfectly conservative, those coupled simulations just fall apart.
So the provocative thought here is that by solving this meshing and single-phase flow problem so robustly,
Yeah, they've essentially unlocked the ability to use these simplified, efficient DFM models for a whole new range of much more complex real-world reservoir challenges that were previously just too computationally demanding or unstable to tackle reliably. That's the real potential here.